Now let's if you can look at please look at the lecture notes channel. I've posted a notes titled orbital perturbation. Okay, so we have done some introduction last time. So what we had so far was we learned that our orbits are not always ideal. Okay, you know, this is our two-body motion. Yeah, so this is ideal. I mean, what you can get from this equation of two-body motion, two-body problem, are the orbits that we have learned before, in a circular orbit, elliptic orbit, parabolic or hyperbolic trajectories. But in reality, we're gonna have some kind of perturbation, which means extra forces that are gonna act on our satellite, disturbing our orbit. So you know that our orbit, you know, we have the 6 orbital element: A, E, I, big omega, the node, the argument of perigee, small omega, and theta. So the perturbation is going to change our orbital elements here. Okay, I've shown you last time that we have we have 4 types of orbital perturbation. Yeah, one is the third body perturbation. The perturbing force is small. This one comes from our third body. I mean, which is not Earth, which is not under satellite, Moon or Sun. It's very small, but it changes a little bit too. Okay. So let me do this. Okay. So, and then the second one was solar radiation. Believe it or not, radiation from the sun can also act as a perturbing force. Just to give you some interesting things, go look up something called solar sail. What is this? I need to move this a bit. There you go. Solar sail. If you have time, you can Google this one. Look it up online. Solar sail. Basically, it's using radiation, solar radiation, to move in space. Interesting, this one. The third one is atmospheric drag. Okay, atmospheric drag does pose a big problem for low Earth orbit satellite. Low Earth orbit. It's very, very significant to those below 800 kilometer altitude. So it's one of the, I would say, the biggest orbital perturbation in low Earth orbit. But today what we're going to do is the one type of orbital perturbation that we haven't really explored so far is what we call J2 perturbation. Okay, and this one is the most interesting one, and I would say it affects all of our satellites, really. Okay, and we look at it, look at your slides, and I've posted, oh, what's that? Capital problem. I think I've posted some slides from the previous lecture. But what is actually J2 perturbation? Yeah, so if you can see J2 perturbation, it is caused by the oblateness of the Earth, which means that Earth is not really a perfect sphere. It is kind of squashed a bit. So the equatorial radius is more than the polar radius. So this squashed sphere, we call this an oblate spheroid. Okay, and because it's not a perfect sphere, and because it's oblate spheroid, then the gravitational acceleration also is not uniform For example, if you have if your orbit, just a simple example, if your orbit is something like this, the satellite will feel different, gravitational acceleration at different point in the orbit. So these differences, these slight differences, will cause our orbit to be disturbed a bit. Okay, why is it called J2? Okay, well, you can do this for every you can look at the shape of every planet, and of course every planet has different shape. And how do we quantify this shape? We use something what we call zonal variation. And zonal variation is an infinite series. It's equation with all coefficients, J2 plus again J3, so on and so forth. Okay, so the most significant one is just J2. Okay, because it's much larger than the other perturbation J3 and J4, J5 and so on. So we only look at this J2, and we call this second zonal harmonics. Okay, so that's why it's called J2. So all you need to know, J2 perturbation is caused by the obliteness of the Earth. Now, like I said, every planet has different shape, different obliteness, and different value for J2. So at the moment, we just look at this one here. For Earth, J2, for Earth, J2 is 0.00108263. So that's our number we're going to use from now on. Okay. All right. So what's so annoying about J2 perturbation is, before I get into the technical part, do you have any question? Let's see. Okay, you can just ask me at the voice channel, or just type it out. Okay, so I'll just take it that Adini will represent everyone then. Okay, so let's get into technical stuff. So what is so annoying about J2 perturbation? Like I mentioned before, when we deal with perturbation, we need to look at our orbital elements, A, E, I, node, angle, the perigee. This one is changing always, so we need to look at this 6 orbital elements. J2 perturbation, okay, changes these 2 elements a lot. Okay, so how much is it changing? Well, you have a formula. J2 perturbation will change your node big omega by this much per second. Okay, so you have to put all this value here. Let's say, for example, your let's say you have your orbit is an elliptical orbit with eccentricity 0.1 and semi-major axis, maybe I don't know, maybe 10,000 kilometers, for example. Yeah. Okay, and you know what mu is. We know what J2 is just now. It was already given here. Okay, 1.08263 times 10 to the power minus 3, and also a radius of Earth. Okay, so if you have such orbit here, okay, with eccentricity 0.1 and the semi-major axis 10,000 kilometers, and you know what the inclination is also, let's say certain degree, maybe 10, you can find out how much your node, how much your Ryan angle is changing over time due to J2 perturbation. Okay, so you need these 3 numbers that defines your orbit first, then you can know how much J2 is actually changing your node in terms of radian per second. And another one is also J2 perturbation also changes your argument of perigee over time. So that's why I put a dot up here. It's the rate of change. Yeah, it's not the argument of perigee, but the rate of change of argument of perigee, and this is also the rate of change of the Rhine angle. It has a similar, well, I would say about similar formula. The only difference is the term being back here. Okay, so again, if you know your eccentricity of your orbit, your semi-major axis, or inclination, then you can plug this in and then see how much J2 perturbation is changing your argument of perigee in terms of radian per second. Okay, so you need to specify this first. So okay, so that's how, you know, you can see that in terms of formula how much J2 perturbation is changing your node angle and argument of perigee. But what does it actually do in I mean physically? Well, if you have an orbit like this, for example, yeah, okay, J2 perturbation that is caused by the obliqueness of the Earth will change your orbit a bit like that. Although it's little by little, but over time it's going to change the orientation of your orbit completely. I mean, you know, it's going to be totally different from your initial orbit orientation. Okay, so the gravitational pull of the Earth's obliqueness causes the orbital plane of an eastbound satellite to swing westward. Swing means that the orbit first it's like this, and then it's changing here over time. Okay, now, okay, let's do some examples. Oh, before I go to examples, let me see if I can find a YouTube video that can show you the Sun-synchronous. Okay, Sun-synchronous. Yep, this one here. So
greetings.
Again, I think I've shown this last time.
The red vector.
Okay, this is how actually our orbit is changing over time. You see, it's changing bit by bit over time, and this is due to the J2 perturbation. Let me see which one is the. And over time it will be completely changes like that. If you see the green one, okay, in this example the green one is the Sun-synchronous orbit. Okay, and if I click in the beginning of the video, you can see where the green orbit is, yeah, and where you can see where the white and red orbit is. But over time, okay, remember those positions, yeah, over time. Can you see it now? The green orbit, red and white orbit. The red and white orbit are not a Sun-synchronous orbit. Okay, you can see how much their orientation with respect to the sun, okay, is changing. But our Sun-synchronous orbit is still synchronized with the view of the sun. Okay, so this is the point of Sun-synchronous orbit, is to synchronize the orbit with the position of the sun at all times. Okay, if you look at the, oh yeah, here we go. Yes, you can see this one. You can see the green orbit in this example here. Over the year, okay, as you can see, one orbit here, the period is 1 year. This is the orbit of the Earth around the sun. You can see the orbit of the satellite, its orientation with respect to the sun is consistent throughout the year. So this is what we call a Sun-synchronous orbit. The orbit of a satellite which is oriented towards the sun throughout the year. Okay, and if you see this one here, the red one, this one is the red one. is not a sun-synchronous orbit. You can see in, for example, in June, the orbit is facing this way with respect to the sun, and in September, it's already, changing like that. See, its orientation with respect to the sun is not the same anymore, and in December, it's not the same anymore. So the red one are not sun-synchronous orbit. The green one is. The application of sun-synchronous orbit we will learn more deeply in our next class next year, probably next. You see if this PKP thing is, I don't know how long it's gonna go, but when you take satellite technology, EAS3812, you will learn more about sun-synchronous orbit and how is it important for our satellite. Let me attend to any questions you have. Okay. Saya tak dapat isi attendance. Yeah, for the attendance you need to log in to your email, UPM email. You know about this, yeah? Before we go examples, let's take some questions if you have. Does the change of orbital elements can cause collision? No, not really. Not really. But if for any unfortunate reason that your orbit is so close to the other orbit, the other satellite's orbit, and then somehow with the combination of things, your orbit coincides with that satellite's orbit, still collision is not likely to happen, really. Is the YouTube animation red describe J? YouTube animation, the red one. Does the red describe J? You mean the red arrow or the red orbit? The red orbit is just an orbit with an inclination of 28 degree. It's not a sun-synchronous orbit. If you're talking about the red orbit, if you're talking about this red arrow thing, this one is pointing to the vernal equinox, which is the I, unit vector I, vernal equinox. But the point that we're trying to show you here is, you can see the sun is always in I think from your left, right? And only the green one, the sun-synchronous orbit, is always somehow fixed to the orientation of the sun. I mean, it's always consistent with its position like that. Okay, but the red and white one over the year is just changing its orientation with respect to the sun. Sun is probably here. Okay. Yeah. I'm just waiting Lee to type. So sun-synchronous satellite too. Okay. Possible? Oh yes, it is possible. Which nicely segue to my next presentation. Okay, so let's do some example, just to show you how to actually design a sun-synchronous orbit. Well, not really design right now. Right now, let's just take an example. Let's say you have a satellite with certain semi-major axis, with certain eccentricity and certain inclination. Okay, so in this case, the inclination is given as some numbers here. Eccentricity is 0.0083891. Okay, 31, and the semi-major axis is some 8 kilometer. Okay, let's say you have an orbit that has these elements. Okay, and then the question is asking, find the nodes regression big omega dot, and perigee advance, small omega dot. In other words, you're given these three orbital elements. Next, what you need to do is to find how much your omega, big omega, the right angle node, and argument of perigee is changing due to J2 perturbation. Okay, due to J2 perturbation. Now you can just plug in everything in the formula and then you'll get numbers. Okay, so you can get a number here. So apparently, if you have such orbital elements, such orbit, J2 perturbation will change your node by minus 1.0465 times 10 to the power minus 6 radian per second. Okay, which is equivalent to 5 degree per day. 5 degree per day. That's quite a lot if you think about it. A year, how much is it changing? Okay, so, and then next one is the argument of perigee. How much is the J2 perturbation change? Wait, let me say that again. So how much J2 perturbation is changing the argument of perigee of your orbit? So apparently it's by this much, 7.9193 times 10 to the power minus 7 radian per second. We change it to degree per day, then it's 3.92 degree per day. Okay, that's quite a lot. Imagine after you launch your satellite this year, and then next year the orientation will be completely different. Okay, so here I've posted up some I think I got this from Curtis' handbook, the textbook. Oh yes, Curtis. So you can see how much actually omega dot, big omega dot and small omega dot is changing per day for different altitude, you know, different altitude, different degrees, and for eccentricity 0.01. Okay, so this is just to show you how much is J2 perturbation is actually, you know, strong enough to actually change your orbit. Okay, so right now, okay, because J2 is annoying, I would say. So how do we actually, can we do something about it? Well, not really, but there are two special cases which I want to show you. Special cases here means that you can actually you can actually design an orbit based on J2 perturbation. Okay, I'm going to show you two examples. One is what I mentioned just now, Sun-synchronous orbit. How do we design a satellite such that, okay, the orientation of our orbit is always consistent with the sun throughout the year? That means if argument of perigee, that means if the node regression is going to change, well, it's going to change consistently with respect to the sun. Now, why is this important? Because sometimes, for example, if you have an Earth observation satellite, okay, that goes around, that orbits the Earth, and Earth observation satellite, usually they have camera, optical camera as payload. When you use an optical camera, you always need the sun to actually to give some light on the Earth. Just like your normal camera, you always need light to actually capture, take a picture. Okay, so in this case, an Earth observation satellite will need the sunlight for its camera, and they need the sunlight to be consistent throughout the year. So it will be the same sunlight in January, same sunlight in March, June, September, December. The sunlight condition, I want it to be the same throughout the year, not changing. So how do I design my orbit such that it will, if the node is going to regress, if our run angle, big omega, is going to change, it's going to change according to the sun, 360 degrees per year, so that you can get the same sunlight. Okay, so this is what I mentioned here. Sun-synchronous orbit is an orbit designed such that it precess means rotate, one complete revolution each year, such that it always maintains the same relationship with the sun. Okay, always receiving the same sunlight condition, for example. Okay, so we, in this case, we'll need some condition, which I'll show you later. The second orbit I want to show you here is special orbit. Is called Molniya. It's a Russian word. I don't know if it's called Molniya or Molnaya, but I've heard people call Molniya, but that doesn't sound Russian at all. The reason is Molniya orbit, this is special. You know, when you have, if your position of your country is in the equator, so if you want to have a satellite to look over your country, so you just launch an equatorial orbit satellite, right? It will always go above your head. For example, if you live in Malaysia or Singapore or Indonesia, you can have an equatorial satellite which will always pass over your head several times each day. But what if your country is somewhere up here? What if you are a Russian? You know, you have country up there. If you use equatorial orbit, then it will be useless, because that you will never be able to see. If you sit here, you will never be able to see the orbit, the equatorial satellite orbit. So they need to design something, a special one. They need to design an orbit which has some kind of inclination like that, so that you can see the satellite. And then, if you design it again, design it more, you will do something like this: elliptical orbit, which has most of the portion of this orbit is at the top here, so that if you're living here in Russia, you always see this satellite more frequently or longer throughout the day. Okay, so this is what we call Molniya orbit. This is basically used for communication satellite in the polar region, or for the Russians. Okay, so but before that, let's look at the sun-synchronous orbit. Let's see if there's any question. So it's the possible. Okay, to answer Lee's question, so how do we design a sun-synchronous orbit? Okay, so here's the condition. If you want to design a sun-synchronous orbit, okay, this value here, I forgot, I think it's mu J2 radius of Earth squared divided by 1 minus E squared, the whole thing squared, and 7 major axis. Is it sine? No, it's cosine. Okay, cosine I. If you want to design a sun-synchronous orbit, this whole thing needs to be equal to this number, 1.991 times 10 to the power of minus 7. The reason is this corresponds to 360 degree per year. Okay, remember, sun synchronous, which means we need to be synchronized with the sun. If you need to be synchronized with the sun, then you need to be able, you need your orbit. Okay, you need your orbit, for example, to be moving with respect to the sun similarly. I mean, it needs to be moving at 360 degrees per year. So if it completes 1 year, so that means the node is always maintained. So if I change 360 degree per year to radian per second, this is what I get. So you need to be, you need to make sure that this value right here is equivalent to 1.991 times 10 to the minus 7 radian per second. So this is what we call the condition for sun-synchronous orbit. So this is the condition. If you want to make your orbit sun-synchronous, you must calculate everything here and make sure it is equal to that. You can change E, you can change A, you can change I, but make sure it is equivalent to 1.991. Example. Say for example you need a satellite to have a period of 100 minutes for whatever reason, and you need it to be sun-synchronous. Okay, you need it to have a period of 100 minutes and sun-synchronous orbit. So how do we design our sun-synchronous orbit? So from this information here, 100 minutes, you know that our period is 100 minutes, which is about 100 minutes, about 60 times 100, 6,000. Oh, I think that's 6,000 seconds. Okay. All right. So that will correspond to A7136.63. So you know your A at the moment. Okay. So like I said, you need to know A, you need to know your E, you need to know your I. So A is already 7136.63 kilometer. What about E? It's a circular orbit, so E is 0. Easy. What about I? We don't know I. We don't know the inclination of orbit to make it sun-synchronous. So we need to find I. So we need to find I such that the orbit is sun-synchronous. Okay, so how do we do that? Again, let's look at the condition before, what we have here, this one, right? Okay, so you put it down here, you key in all your known values, 398600, J2, and this is radius of Earth. You know that the eccentricity is 0, is that the only thing that is unknown is I. Okay, and you need to equate that to this number here. This is the condition for sun-synchronous orbit. Solving for the inclination angle, you'll get I 98.43, which means if you need to have a satellite, a circular orbit with period 100 minutes, and you want to make it sun-synchronous, well, you need the inclination to be 98.43 degrees. Okay, you will see afterwards, if you do more examples. For example, sun-synchronous orbit is usually above 90 degree. Okay, very nearly polar orbits. So if you get something like number like this, 90 something, that means it's correct. So let me stop here for sun-synchronous orbit. Yes. Select exploration. For sun-synchronous orbit, do you have any question? Okay. Kenapa Adam? Sekejap. Ada orang tak boleh masuk. Okay, all good. Alright, thanks. So that I know I'm not talking alone here. Okay. Alright, so that is sun-synchronous orbit. So basically, if you this equation up here, the omega dot, big omega dot, can be used to design sun-synchronous orbit with the condition that omega dot needs to be equal to this number right here, and then you can set your own A, E, and I for your orbit. Next one, I promised you I want to show you Molniya orbit. So let's another introduction for Molniya. Molniya, it means lightning. Okay, it's a military communication satellite system used by the Soviet Union for the reason I mentioned to you just now. They want to have a satellite which can stay above their head as long as possible. So if you have an equatorial orbit, well, that's not possible for them. If they want to have a geostationary orbit, that is also not possible for them, because remember, geostationary orbit is always the inclination is always 0 for geostationary orbits. So they can't have that. So they figured out, we need to design something. Okay, I don't know how to make a Russian accent, but I guess that's what they are thinking. So someone from the military, for example, maybe, or one of the scientists came up with the Molniya orbit. Basically, it's a highly elliptical orbit, which has its apogee down here. This is apogee, perigee, and apogee up here. You remember, yeah, Kepler's second law. If for the satellite will spend less time here at perigee, I mean it goes really fast here, but it stays very long up here. Okay, so this is very useful. This type of orbit is very useful for the Russians because it stays in this part of the orbit longer than in its perigee, so they can see their satellite most of the time. Let me see if I can find some interesting ground track. There you go. Let me see. Yeah. Love this one. Okay. Oops, what happened? Did I press the wrong button? Yep, I did. Let's look at this. The yellow one is Molniya orbit. So if you were to trace the ground track, okay, of a satellite in Molniya orbit, you can see it's spending so much time in the Russian sky, and you see it's going, because that is the apogee. You see, so, and then when it gets perigee really fast, it goes back up again, and now it's spending so much time on the Russian sky. Okay, it just occurred to me that actually they spend on the American sky and the Russian sky equal time. No wonder this is a useful communication satellite. Okay, so can everyone see the the YouTube video just now? Don't worry, the Molniya orbit has been around for so long, so probably they have used that for spy missions. I don't know. Does the communication stops? Well, it's just satellites. It depends on them how to do that. Adini asked question: what happened when the satellite is not on top of their heads? Well, just like I showed you just now, it will travel to some other part of the Earth, but it will come back soon. So usually, the Russian will, I think they will have this one satellite in Molniya orbit will spend about 8 hours in the Russian sky, if I'm not mistaken, and only 8 hours per day. 8 hours per day. So what they do is they have 3 satellites in one Molniya orbit. Oh, sorry, 3 satellites in Molniya orbits, 3 different Molniya orbit, so that they have at least 1 satellite at each time. Can you get? Do you get it? So Molniya orbit, Molniya satellite can spend only 8 hours per day on the Russian sky. So if you have 3, you can design such orbit to, you know, the first 8 hours this satellite, the second 8 hours another satellite, second satellite, the third 8 hours the third satellite. Let me see if I can find something on wiki. Here you go. Okay, so they will have satellites like this, 3 different satellites in Molniya orbits. Okay, so that they will have at least 1 orbit on the Russian sky at one time. Haha. So this a lot of interesting thing you can do with you know, if you know how to design the orbit. Yeah. Whoa, language, YB, language. Okay, so alright, so let's learn from the Russians. How do we design a Molniya orbit, just in case? Okay, the reason I want you to know about this one is because it is interesting. Now the one is it exploit the J2 perturbation. Well, not really exploit, I would say. It finds a way to avoid avoid, in quotation marks, avoid the effects of J2 perturbation. Okay, so what is this? Oh man. All right, so what are the conditions for Molniya satellite, Molniya orbit? Okay, so usually what they do is they will set their argument of perigee at 270 degrees. Okay, for optimal visibility, they want to set it at that argument of perigee. Eccentricity is highly eccentric. Usually it's between 0.69 to 0.74. The right angle, the node, can be any number. Okay, and semi-major axis is usually 26,000 kilometer. Usually, this is because they want the period to be about 8 hours. Sorry, 8 hours, is it? I think so. I think it's yes, about 720 minutes. So okay, so the problem is right now, J2 perturbation, like I said, they are annoying. It perturbs omega, right? You remember that we have blah 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 equals to whatever. Okay, you remember this equation, this formula, yeah? So J2 perturbation does change this number every second, but you as a Russian orbit designer, you don't want this to change. I want this to be 270 degrees. I want it today, I want it tomorrow, I want it next year. I don't want it to change. I want my argument of perigee to be constant at this point, 270 degrees. So if you are a Russian astrodynamicist, what you would want to do is you want to set your Molniya orbit to be such that omega dot, the rate of change of argument of perigee, is 0. The reason is, like I said just now, you don't want this to change. I want it at 270 degrees. I don't want it to change. You know, node angle can take any value between 0 and 360, but argument of perigee, I want it to be stay at 270 degrees. So I want the rate of change to be equal to 0. So if you are a Russian orbit designer, how would you design your Molniya orbit? Okay, so what you do is, again, you take the equation number 2, one of the formulas just now, you write down everything. Okay, so now you can see that you already have your A from the initial design. Okay, you want that the period to be such and such, so A is that. So you plug that number in here. Okay, E, maybe you can take any number between this. Okay, 0.6974. Okay, but you're not sure about the I. So this one you're not sure. Okay. So you plug in everything. Let's say E is 0.7, I think. I just pick a number. Your inclination angle, you will have two answers. You will get around 63 degrees or 116 degrees. So basically, if you were to design a Molniya orbit which has this condition right here, omega dot equals to 0, you'll find two solutions. Only two solutions. Either I inclination equals to 63 point something, depending on your eccentricity, or 116 degrees. 63 or 116 degrees. Okay. Usually, Molniya orbit are designed to be a prograde orbit. It moves with the rotation of the Earth. So usually you'll choose this number right here, 63.43. So that's how you design, you find the inclination of a Molniya orbit. First, you set omega dot equals to 0, and then you write down the equation. Okay. You write down everything, I minus 2, and you set it equals to 0. Now, if you know this, you can get from here, this number right here. You know E, you can pick any number between this. Okay, J2 is given, RE is given, this one is given already. All you need to do is just find I, and you will find two solutions of inclination, but usually you will choose a prograde orbit. So that's why you see the inclination of a Molniya orbit is always around this number, 63.43 degrees. Okay. All right, so that is all for today. So far we've learned how to design three types of orbit. We've learned how to design a geostationary orbit. This one is the easiest. Secondly, we've looked at Sun-synchronous orbit. Thirdly, we look at Molniya orbit just for fun. Okay, so I think if you look at the one of pin messages, geostationary orbit is a circular orbit. So we know how to design geostationary orbit. It needs to be circular, its inclination needs to be 0, and its period needs to be a whole day, 23.96 hours. That's geostationary orbit. Sun-synchronous orbit, how to design it, you've seen the condition just now, yeah? The big omega dot needs to be equal to certain number, 1.9 something. And Molniya orbit is a bit complicated, but the essence is you need to make the rate of change of argument of perigee to be 0. So that's how you need it to be. You need to that's how you design Molniya orbit. Okay, so with that, I think that is the end of our session today, and end of the chapter orbital perturbation. Probably, if you were to do anything in this chapter, we will do some exercises on how to design orbit, for example, or if we have an orbit, just to see how much is the orbital elements are changing throughout the year. We can do that, okay, with the analysis, the formulations that we have learned before. So that is all for today. Thank you very much. I'll just attend any questions if you have one. Doctor, why period of Molniya orbit needs to be around 27? I think let me see, 70, I think yeah, around 720 minutes here, 718 minutes. So I think it's because see, there's a paper by some Russian scientist here. So let's see, period. The reason I mentioned 8 hours just now, that one is if you want to have 3 satellites, sorry, if you want to have let me say that again. If you want to have 3 satellites to be like a relay satellite, one after another, then probably your period will gonna be 8 hours. But I think usually the Molniya orbit here, space vehicle on my orbit, let me show it to you, launch into spatial highly orbit with a period of 12 hours. Okay, so usually they will want to design such a way. If you were to design it in 8 hours, I think you can, but probably well, for sure your semi-major axis is gonna be smaller, but again, this number here, 12 hours, is it depends on the designer themselves. So perhaps the Russian scientists, they want the 12 hours. Okay, I think I don't remember the reason why it was 12 hours. If I can, because I think last time I thought this was 1 year ago, so I'll check back with you. Okay, so yes. Okay, not necessarily 8 hours. You can create a Molniya orbit with this semi-major axis smaller or bigger, but usually they want to design it that way. So that's how we get the semi-major axis 29,000 something, 26,554. Yes. Okay. All right. Is there any other question? If not, then okay, I'll just, yes, Adini, by the way, okay, go to menti.com and use the code 414549 and tell us anything about the class, anything about your day, anything about your feeling, whatever, using 3 words or less. So I got one here: thirsty, hungry, and dahaga. Okay, no, that's okay. Hari ni it's okay if you wanna ask me private pun boleh. Alright, do we have in Malaysia have what, Molniya? No, we don't need Molniya orbit. We are happy living in equatorial orbit. In the equatorial region, so we only need geostationary satellite for all communications. Hot, very hot, very, very hot. That's like 1, 2, 3, 4, 5, 6. That's 6 words. Curious, excited, blur. Okay. All right. For those of you tired hot rewatch, house squiggly nuggets. Okay. All right. You're welcome, Yamunan. Okay. Alright. Esok ada kelas juga hari ni. Yes, macam biasa. We do it at our usual time lah, 11 to 12. So yikes. Okay, you're welcome everyone. Alright, bye bye. Okay. By the way, I'll just